let's start by reviewing what we learned in the past 3 lectures. Okay, so we learned a lot about the phenomena that is related to magnetism. Okay, so first we learned bar magnet. Okay, so bar magnet has a north pole and a south pole. The north pole will attract south pole. The north pole will repel north pole. Okay, and the south pole will repel south pole. Okay? And we learned about the magnetic field lines of a bar magnet. Okay, so the magnetic field direction is defined as the direction that a compass north pole will point towards. Okay, so for a bar magnet, outside the magnet, the magnetic field lines will start from the north pole, it go through a loop and go back to the south pole. And then inside the bar magnet, the magnetic field lines goes from the south pole to the north pole. Okay, so at the end of the day, we have always a closed loop for magnetic field lines, which is very different from electric field lines. Okay. And we learned that two kinds of things can feel a magnetic force inside a magnetic field. Okay, so the first of all, there is moving charges. Okay, so if we have a charge, it's moving at a velocity, so there's a velocity vector, and then it's inside a field. Okay, there is a magnetic field vector. The charge will actually feel a magnetic force. Okay, so the magnetic force is actually QV cross B, right? So the magnitude is QVB sine theta, okay, where theta is the angle between the velocity vector and magnetic field vector B. Okay, so it's sine theta. Sine theta means that if velocity is perpendicular to the field, then there is maximum force. If velocity is parallel to the field, theta equals 0, sine theta equals 0, and then there's no magnetic force. Okay, and importantly, how do we find the direction of the force, of a magnetic force for a charge? Okay, so there's a right-hand rule. We point our fingers towards V, and then we curl our fingers towards B. We use our right hand, and then the thumb will point towards the magnetic force direction. This is a right-hand rule. And this works for a positive charge, and for a negative charge, there is a negative sign. So we flip the direction of the force. That will be the direction for the negative charge. Okay. So magnetic force on a moving charge, QV cross B. Okay. And we learned that important distinction between charge moving in an electric field and charge moving in a magnetic field. Okay, inside the electric field, if the electric field is uniform, then a charge will always feel a force of QE, right? And the force is always the same magnitude and pointing towards the same direction. Okay, so if the direction is different from initial velocity, then there will be a constant acceleration, and the charge will be moving with a constant acceleration. Okay, so it will be moving along a parabola. While if a charge is moving inside a magnetic field, okay, in a magnetic field, if the velocity is perpendicular to the field vector B, then we know that we use our right-hand rule. Okay, we point our fingers towards the velocity, curl around towards the magnetic field. We get the direction of the force. Okay, and the force is perpendicular to the velocity, so it provides a centripetal acceleration for the charge. So a charge moving inside the magnetic field will move in a uniform circular motion, okay, where the magnetic force provides the centripetal force. QVB equals mv squared over r. Okay. And we learned that if there's both magnetic field and electric field, then there's both QVB and QE. And if we choose the correct direction, the proper direction for electric field and magnetic field, we can balance those two forces so that the charge will keep as still or moving at constant speed, right? And then we learned that current is basically the flow of charge. Okay, so a current carrying wire will also feel a magnetic force. This force is ILB sine theta. Okay, well, theta is the angle between the current and the field. Okay, so again, we have a right-hand rule. Okay, we point our fingers towards the current direction. We curl our fingers towards the field direction. Then our thumb will point towards the force direction. ILB sine theta. And after this, we learned that three things can generate a magnetic field. Okay, so we learned the magnetic field distribution around the bar magnet. Then we learned the magnetic field direction along a straight wire. Okay, so if there is a straight wire, it carries a current. We point our right-hand thumb towards the current direction, and then the fingers will be curling around the field direction. So basically, around a current carrying wire, straight wire, there will be loops of magnetic fields. Okay, and the strength of the magnetic field is proportional to the current, inversely proportional to the distance, mu naught I divided by 2 pi r. Okay. Mu naught is the permeability of free space, is a given value, 4 pi times 10 to the minus 7 Tesla meter per ampere. Okay, and because wires can generate a field, okay, can generate all the loop fires, loop fields around it, and then the current can also feel the force inside inside the magnetic field. So if we have two currents, they both will generate a field, and they will both feel a magnetic force. Okay, so we derive that this magnetic force is proportional to both currents, I1 and I2, and inversely proportional to the distance. And if the two currents are flowing towards the same direction, we derive that there will be attraction between those two wires. Okay, if the current is flowing towards different opposite direction, then there will be repulsion between those two wires. Okay, and so this is current flowing in a straight wire. We use right-hand rule to determine the direction of magnetic field loops. Okay, we also can have current flowing in a loop. Okay, current flowing in a loop. When the current is flowing in a loop, the magnetic field distribution basically similar to a bar magnet. Okay, so at the center of this loop, we can determine the direction of magnetic field if we curl our fingers of right hand towards the current direction, and the thumb will point towards the field direction. Okay, so when we have a loop and there's a current flowing through the loop, we can usually consider it just like a bar magnet. Okay, and we know the magnetic field strength at the center of the loop is also proportional to the current, inversely proportional to the radius. Okay, and it's also proportional to the number of loops in here. Okay, this is just right-hand rule. And once we know that the loop flowing a current is basically a bar magnet, we can talk about the interactions between different loops. Okay, they can be either attractive or repulsive, depends on the direction of current. Okay, because the direction of current tells us the direction of the field. Okay, and furthermore, we learned a third case that a magnetic field can be generated from current. This is a solenoid. Okay? So inside a infinitely long solenoid, there is a even magnetic field. Okay, this magnetic field is proportional to the current I, and is also proportional to the number of turns per meter n, lowercase n. Okay, so we learned that if we make a solenoid and give it a current, we will have a uniform magnetic field. The direction is due to, again, the right-hand rule. We curl our fingers of right hand along the current direction in the solenoid, and then our thumb will point towards the field direction. Okay, so recall that we can also generate an even electric field if we have two plates even with even distributions of positive and negative charges, we'll have a even electric field between those two plates. Okay, so in this case, we have a solenoid of many loops of current. They extend a length of L. It has lowercase n turns per meter. Then we have a magnetic field. Okay, we have a uniform magnetic field only inside the solenoid, and it's mu naught Ni. Okay, and in the last course, we talked about the magnetic flux and the Faraday's law of induction. Okay, so basically, we learned quantitatively there is a magnetic flux. Okay, so magnetic flux is the dot product between a field and an area vector. Okay, so if we have a certain area, the area vector is perpendicular to the area. Okay, so if we have a loop, the area vector is perpendicular to the loop. Okay, area vector is perpendicular to the loop. And we talk about the magnetic flux, which is the number of magnetic lines going through a given area. This is the area. Okay. So we know that if the area is perpendicular to the magnetic field, then the area vector will be parallel to the magnetic field. Okay. In this case, the angle between the area vector and the magnetic field will be 0, and cosine theta will be 1. Okay, so in this case, we have maximum magnetic flux of BA. On the other hand, if our area is parallel to the magnetic field, then our area vector is going to be perpendicular to the magnetic field. Okay, so in this case, there is no magnetic field lines going through the area, so magnetic flux is 0. Okay, so in the general case, we have BA cosine theta, where the theta is the angle between the magnetic field and area vectors. Okay, now we learned the magnetic flux. We learned Faraday's law of induction. So quantitatively, if there is a magnetic flux change, okay, we calculate the flux change rate over time and multiply the number of loops. We get the induced EMF, okay, electromotive force. Okay, and further, there is a minus sign telling us the direction of this electromotive force, okay, which is further defined by the Lenz law. Okay. So one thing we didn't talk about is that so magnetic flux is basically BA. Okay, B is in Tesla, A is meter square, and you divide it by a time. Okay, which is in seconds. So why does it result in something that is in volts? Okay, so Tesla meter square, which is delta phi, divided by delta T, which is second, it should give us volt. Okay, so to understand this, we recall that what is Tesla? Okay, Tesla is a unit of field, right? So the field is related to force by F equals QVB. Okay, so 1 Tesla is basically 1 Newton per Coulomb and divided by meter per second. Okay, so it's F divided by QV, and we further multiply by meter square and divide by second. Okay, so what we get is that the second is cancelled, meter square, meter is cancelled, and we get what we get. We get Newton times meter divided by Coulomb. Okay, and furthermore, Newton divided by meter. Okay, force divided by distance is joule, right? It's an energy, and joule per Coulomb. Okay, what is joule per Coulomb? So recall that electric potential difference is basically electric potential energy difference divided by charge. Okay, so joule per Coulomb is basically volt. Okay, so the unit matches. Okay, so if you have Tesla per meter square divided by second, you get volt. There are many applications of this, but importantly, we need to know the direction of the induced current, okay, if the magnetic flux changes. Okay, so the Lenz's law tells us the induced current always flows in direction that opposes the change that causes it. Okay, so the induced current will induce a magnetic field, and this induced magnetic field will always oppose the change. Okay, so for example, if a bar magnet is moving to the right, then the magnetic field towards right is increasing. Okay, so the induced current needs to generate a field towards left. Okay, needs to generate so that the field would not increase that fast. Okay, if the bar magnet is moving towards left, then the field pointing towards right is decreasing. Okay, so the induced current needs to generate a field that is pointing towards right, so the field doesn't decrease that fast. Okay. So with this, we can determine the direction of the induced current. Okay. And we further described this case where we can talk about everything quantitatively. Okay, we have this circuit is inside a uniform magnetic field, and then part of the circuit is moving at the speed v. Okay, so we can think of this part that's moving, the length is L, and then the circuit, the other part, the length is D. Okay, so the part that has magnetic flux changing is this part, this area. Okay, the magnetic flux is changing because magnetic flux is BA cosine theta. Okay, B is not changing, cosine theta is not changing, but A is changing. Okay, and the rate that magnetic flux is changing in here, delta phi divided by delta T, we derive that is basically B times L times delta D divided by delta T, right? And delta D divided by delta T is basically BLV, okay? So this is the absolute value of the induced electromotive force. Now you have a quantitative description of it, of the induced electromotive force. You can apply Ohm's law to calculate the current. Okay, and you can use Lenz's law to find out the direction of the current. Okay, and now you have a current and a field. You can talk about the force. Talk about the force with the right-hand rule of F equals ILB. Okay, so in this simple setting, we can talk about everything we learned related to magnetic induction. And we further talk about the eddy currents. Okay, so if the metal is feeling a magnetic flux change, it will induce a current inside the metal so that it opposes the change of magnetic flux. Okay, this current is usually flowing in a loop and is called the eddy current. Okay. So the last thing we learned last time is about transformers. Okay, the transformer, we have a primary circuit and a secondary circuit, and what's flowing in here is a AC alternating current voltage. Okay, so the voltage is always changing over time. Okay, so which means the current is changing over time and the flux is changing over time. Okay, remember the flux is B times A, and B is from this current. Okay, B is for a solenoid, B is proportional to the current. Okay, B is basically mu naught times number of turns per meter times current. Okay, so now we use this iron core so that all the magnetic flux, okay, all the magnetic flux will be shared between the primary circuit and the secondary circuit. Okay, so we basically collect all the magnetic field inside this iron core, so that the primary and secondary circuit shares the same delta phi over time. Okay, so we derive that in this case, the transformer can change the AC voltage, right? And the output voltage is proportional to the input voltage, proportional to the output number of coils, and inversely proportional to the input number of coils. Okay, so if we have more coils on the right we will increase the voltage. Okay, if we have less coils on the right, we will decrease the voltage. Okay, the voltage is just scaled as number of coils on the right divided by number of coils on the left. Okay, so this is the principle of transformers. In this five last lectures of this course, we're going to talk about this phenomenon called wave. Okay, so today we're going to talk about it's basically an introduction to the nature and properties of waves. We're going to categorize waves into transverse waves and longitudinal waves. We're going to talk about quantitative description of the propagation, and then we're going to talk about specific phenomena like interference and stationary waves. And then in the next lecture, we're going to specifically talk about those sound waves. Okay, and then in the last three lectures, we're going to focus on light waves, and we're going to talk about geometrical optics. Okay. So today is basically an introduction. We will talk about different types of waves. We categorize waves due to their nature. We can also categorize due to different directions of waves. Okay, so and then we talk about specific phenomena of waves, for example, the reflection, and then there's a specific property of wave called superposition that gives rise to this special phenomena called interference that happens in the waves. Okay, and at the end we are going to talk about a specific type of wave due to interference is called standing waves. So what is a wave? What is a wave? Sorry, this away. Okay. In general, we can think of this kind of motions, right? So, for example, we have those water waves. So, if we go to the seaside, we can see that there's continuously water waves in the sea. Okay, so how does water waves move? It moves from like far away from the shore to close to the shore, right? So we see that there is a peak of water and it moves in time and it gets closer and closer to us. Okay. And then we can also look at the people who is floating in the water, and they basically didn't move too much. Okay, they move around their positions, but the water can actually move from very far distance to the seaside. Okay, and we can also look at those waves of human. Okay, waves made by human. So each human is only standing up or sitting down in their own seat. But then we see that this peak of human can actually move across the cloud of people. Okay, so a wave, there are basically two things. Okay, there is a disturbance. Okay, for the water, there is a peak. For the people, there are people standing up, and this disturbance can actually propagate in space. Okay, it propagates from one place to another. Okay, for the water wave, it can travel through different spaces in the sea. Okay, and for the people wave, okay, it can travel from one side of the stadium to the other side of the stadium. Okay, so there is a two things in here. There's a disturbance. Okay, the disturbance then propagate. Okay, there's a disturbance and there's a propagation. Okay, and there are we can talk about different types of waves. Okay, categorized by their different nature. So for example, there are mechanical waves. Okay, mechanical waves are governed by Newton's laws, uh, and they can exist only within a material medium, such as water, air, and rock. Okay, so if water moves in a wave, okay, there's a disturbance in water, it propagates in space. This is called water wave. Okay? And apparently, this is just movement of water, so it's basically mechanical. It's governed by Newton's laws. Uh, and we can talk about force, energy, velocity, acceleration, this kind of things in here. Okay, and another thing is like sound waves. Okay, sound waves are basically we'll talk about them in the next lecture, but it is also a a disturbance in the material medium, and then it can propagate in time, in space, right? So if I speak at one end of the lecture hall, the sound wave can actually propagate through air to the end of the lecture hall. Okay, but if we pull vacuum, then the sound wave cannot travel anymore because it is a disturbance of material medium. A third thing is about seismic waves. Okay, this is when you have earthquake. We have earthquake. Basically, there's a source of earthquake. In the source of the earthquake, there is a movement of Earth, right? A movement of Earth can actually travel in the Earth from the source uh, uh, towards a very long distance. Okay, so this is a disturbance of Earth, and it travels in Earth, and it is called seismic waves. Okay, so those are the different types of mechanical waves. And beyond mechanical waves, there's also electromagnetic waves. Okay, so those waves are generated due to what we talked about in the last lecture. Basically, you generate electricity from magnetism, you generate magnetism from electricity, right? If you have a charge that's moving, it forms a current, it gives us a magnetic field. Okay? If you have a magnetic field that's changing, it changes the magnetic flux and it induces a current. A current is basically movement of charge. Okay? So these electromagnetic waves actually require no material medium to exist, so they can travel through a vacuum. Okay, and they actually travel through the vacuum at the fixed speed. This is uh, 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 you can look at it. This is a fixed number because we define the meter and second in this way. Okay, so the speed of electromagnetic waves is how many is this? This is basically 300,000 kilometers per second, right? 300,000 kilometers per second, which is very fast. Okay? So there is a spectrum of electromagnetic waves. The region that's visible to us, the region that can be seen by eyes from red to purple are visible light. And then beyond visible light, there's ultraviolet light, there's infrared light, there are radio and television, radio waves, television waves, microwaves, X-rays, and radar, and those are just different electromagnetic waves with different frequency and different wavelengths, but they share the same speed, and the speed is about 300,000 kilometers per second. And basically, those are two kinds of waves that people know very well. Okay, and in the 20th century, okay, people find that there is another kind of waves. Okay, so it has been a long debate in the history whether light is a particle or is it a wave. Okay, so uh, there are many evidences that light is a particle. For example, if light hits a detector, we can count how many photons, how many particles of light we have. Okay? And there are also evidences that light is a wave. For example, we can do interference. Okay, if we have light going through two slits, they can actually interfere with each other. We're going to talk about this phenomenon of interference in this lecture. But is light a particle or a wave? Okay. Actually, in the 20th century, with the invention of quantum mechanics, people realized that a matter could also be a wave. Okay, so matter and wave are not contradictory, and they can exist at the same time. Okay. So, for example, the electron is usually considered a matter, but we can also determine its wavelength. Okay, so if we put electron through two slits, they can also interfere. So electron can be also considered as a wave, and we call it is discovered by de Broglie, so it's called de Broglie waves. Okay, you can also call it matter waves. And we also have like protons, those small particles. They basically both matter particles and they are waves. And in the recent days, we proved that even larger particles can also behave like waves, like atoms and some molecules. Okay, for example, we have C60. There are 60 carbon atoms inside the C60 molecule. Okay, and this C60 molecule can go through two slits and they can also interfere. Okay, so that's telling us that those matter particles are basically also waves. And this is related to quantum mechanics. So we're not going to go into depth about this. Okay, so basically, if we describe the waves and categorize them due to their nature, we have mechanical waves governed by Newton's laws, and they travel inside a material medium. And we have electromagnetic waves. They can travel through a vacuum, and their speed is given. And then we also have matter waves. Okay, so all the fundamental particles are also waves. Okay, and we can also categorize a wave by another method. Okay, so remember that a wave is a disturbance. Okay, and the disturbance propagates in space. Okay, so we can talk about the direction of the disturbance. Okay, or displacement of individual particles, and then we can also talk about the direction of propagation. So there are two directions in here. Okay, and we can categorize waves due to the directions of displacement and propagation. Okay. For example, we have this string. String is made of lots of molecules, and it can when we can make a disturbance in the string, and the disturbance can propagate in space. So we can make a wave in the string. Okay. And this wave is, of course, a mechanical wave. Okay, we can talk about force, acceleration, energy, this kind of stuff in here. And it's governed by Newton's laws, and it travels only through a string, right? So it only travels through a material medium. So when we're talking about the string and the wave on the string, we can basically, sorry, let me find out this. We can basically talk about the propagation direction, right? So if we vibrate one end of the string with up and down motion, that will generate a wave and it propagates. Okay, and we know that it propagates towards right. Okay, so this is the direction of propagation. But then if we look at a fixed spot on this string, okay, we'll see that this spot is basically moving up and down. Okay, it's moving to here, and then in the next time slice, it will move down, basically something like that. So the displacement or disturbance is actually moving vertically, right? So the vibrate end of string to generate a wave. So this is saying that if we look at any point, okay, if we look at this point is also vibrating vertically. Okay? So this is kind of strange, right? So if we have a string, and string consists of lots of points, okay, lots of points, and each point is only doing a motion in the vertical direction, in the y direction. Okay, but the phenomena of wave is actually moving towards horizontal direction, right? So this is called the transverse wave. Okay, so the displacement is perpendicular to the direction of propagation. Okay, so in this case of a wave on the string, the propagation direction is towards right, and the displacement direction is up and down, right? So they are perpendicular. And we also have a lot other examples of transverse waves. Okay, for example, light wave is actually a transverse wave, uh, and radio waves is also a transverse wave. Okay, we talk about this. So basically, they are the same kinds of waves, right? The light waves and radio waves are both different types of uh, electromagnetic waves, and they share the same nature. Okay, so if we look at a certain spot in the light wave, okay. Uh, and look at its electric field, the electric field and magnetic field, right? So we in here we denote the magnetic field by this blue uh, blue lines, and the electric field by those red lines. Okay, we can track the magnetic field. For example, for this point in the light wave, the magnetic field is only moving up and down. Okay, so in one moment it will be here, next moment maybe here, next moment here, next moment here, and then going up. After it goes up, it then goes down, but it only vibrates up and down. Okay, so if we look at the electric field, those red lines, okay, it only vibrates in this direction, but then the light propagates in a third direction, right? So the propagation direction of light is actually perpendicular. Okay, so the propagation direction is this direction, magnetic field, this direction, okay, this direction, and electric field, this direction. And all of them are perpendicular to each other, okay? So we basically have a electromagnetic wave and it's a transverse wave because the displacement direction is perpendicular to the propagation direction. Okay, let's keep going. There's a demo in here. Click. So this is a matter wave. Okay, so we disturb this thing called slinky. Is basically a spring. We fix one end and we use our hand to disturb the other end. We create a matter wave. Okay? And the matter wave is the disturbance of the slinky, and it can travel inside the slinky. Right? So we can generate this pulse. And we see that for each dot, okay, for each point inside this slinky, okay, for this point, if we track it in time, we will see that this thing is actually moving up and down. Okay, for example, at the next time it moves to here. Okay, so it's moving in this vertical direction, but then we see that the wave is actually traveling in the horizontal direction. Okay, so it's perpendicular and it is a transverse wave. Okay, it's a transverse wave. So we can see that the disturbance is propagating towards right. We can also generate another kind of wave. So you can see this wave is actually different. Okay? This wave is different. So in this wave, this is called the longitudinal wave. We can see that each point of this slinky is moving left and right. Okay? And the propagation direction is also towards right. So they are parallel to each other. Okay, so this is propagation, and this is displacement, right? Displacement. Okay, so we can take a look and we see that, okay, for each spot in this slinky is moving left and right, and then we see there's a wave moving towards right. Okay. So there are two kinds of waves that you can generate with this slinky. Okay, we'll talk about this longitudinal wave later. Okay, so let's still talk about this transverse wave. Okay, so in the transverse wave, okay, so we can talk about the propagation direction, propagation towards right. This is the propagation direction. And then we talk about the displacement direction. Again, this should be perpendicular to each other. Okay. And what else is in here? So we can track a point, this red point in here. Okay, this red point in here. This red point in here at next time. Okay, so if we go down, we basically travel in time, right? So at the next time slice, it moves down, and then in the next time slice, move to the lowest point, and then it travels back to the middle point, and then it travels to the top point. Okay. So this point inside this transverse wave is only moving up and down. Okay, but then if we track the peak, okay, the peak of the wave, okay, we see that the peak of the wave is actually moving towards right in time, right? So if we look at the peak, is actually moving towards right. Okay, so this is what we're talking about. So if we track the peak or the wave phenomena, it actually move. There's a propagation direction, okay, and in this case, it's propagation towards right. But then if we track a single spot on this wave, it actually just move up and down. Okay. Okay. Uh, let's continue. Okay, and then there is a second kind of longitudinal wave. Okay, longitudinal wave, the displacement of individual particles is parallel to the direction of propagation. Okay, so we draw here a sound wave. Okay, so sound wave are basically generated by this speaker. Okay, and the speaker has a film on it. The film is vibrating back and forth, okay, towards left and towards right. And it compresses and rarefies the surrounding air. Okay, so it makes molecules move around its position. Okay, so if, for example, if you track a single molecule, it actually moves towards right and towards left. Okay, and moves back and forth around this equilibrium position. And these regions of high and low density propagate away from the speaker with the speed of sound. Okay, if we look at individual particles, it will oscillate back and forth uh, around a given position. Okay, if you look at this single particle, it moves back and forth. But then if we look at the peak, okay, the peak is in here, peak is in here, peak is in here. The peak of the sound wave is basically the compressed region, okay, where the molecules move close to each other. We can see that the peak actually moves in time. Okay, peak actually moves in time. And we can also track the valleys. Okay, the valleys are basically the parts where the parts in here where the molecules are moved far apart. Okay, so it's a rather sparse region of the air. And if we track it in time, we will also see that those patterns will move towards right. Okay, so in this longitudinal wave, basically sound wave, the displacement is left and right, and the propagation is also towards right. So the displacement is parallel to the direction of propagation. So it is called a longitudinal wave. And we already demonstrated this. Okay, so if you have a slinky and you move one end up and down, then you will create a transverse wave. Okay, you create a transverse wave. And then if you push it back and forth, then you will generate a longitudinal wave. Okay, in the longitudinal wave, the propagation and disturbance direction are the same direction, right? And in the transverse wave, the propagation and the displacement direction is perpendicular to each other. Okay, and if we plot out the x-axis as position, y-axis as density of molecules, and we know that with high density, we basically have more collisions and more pressure. So if we track the pressure or density as a function of position, we basically have this kind of sinusoidal functions. Right? It looks like a sine or cosine function. And this is a more straightforward demonstration. We can track. We can track. First of all, we can look at those patterns, right? The patterns of the peaks actually moves in time, right? Moves in time. So okay, so those patterns of peaks moves in time. But then if you track single particles, okay, the single particle only moves around its equilibrium position. Okay, so you can see that this red particle is moving back and forth, but only around its original position, right? But then this whole wave, this peak of high density regions will actually move towards right at a given speed. Okay, so there is a speed of wave propagating towards right. And because those two directions are parallel, this is a longitudinal wave. Okay, we can also track it like this. Okay, we make a lot of time slices. Make a lot of this is time 0. This is 1/8 of a period, and then this is a period. Okay, So we can track a single molecule in here. The single molecule is moving towards left first, and then is at 1/4 of the period is the most left, and then at 1/2 of the period goes back to the middle, and then keeps going towards right at 3/4 of a period it goes to the most right, and then it goes back to the left, and at the period it goes back to the original position, something like that. But then if you track, for example, the sparse region, okay, the value of this wave in time, we can see that it actually moves. And the sparse region actually moves towards right, okay, and there's no going back. There's no going back. It just continuously move towards right. Okay, and what else do we see? What else do we see? We see that okay, after a certain amount of time, going from 0 to t, we call it period. This, if we look at this position, it was originally a sparse region, and after time t is another sparse region. Okay, but this new sparse region is basically moved from the left. Okay, so it keeps moving like this, moves to here, and then keeps moving towards right. Okay, and then finally it moves, it replaces the original sparse region. Okay, so after a period of time, the wave can repeat itself. Okay, and during this period, the wave also propagate by a certain distance. We call it a wavelength, and we usually denote it by lambda. Okay, this is a wavelength. And we can also study the case of water wave. Okay, is water wave a transverse wave or longitudinal wave? Okay, so we can have this pond and a body of water. We throw something inside the water. We generate a disturbance. Okay, at the origin. And this disturbance of water can propagate through space, and it propagates towards all the directions. And because it's all water, it basically propagates at the same speed, and it gives rise to this uh, circular pattern. Okay, circular pattern. If you look at the peaks of this water wave, basically they form concentric circles. They're circles because they propagate the same speed towards all the directions, and they're concentric because there is a single source. Okay, a single source where we throw the object and disturb water originally. Okay, and if we track the valleys are usually called troughs. The valleys also form the concentric circles. Okay, if you track the peaks sometimes called crests. Peaks form concentric circles. And those are the propagation directions, right? Those white arrows show you the propagation direction. But to determine whether it's a transverse wave or longitudinal wave, we need to know the displacement direction. Okay, so we look at the single point inside this water wave. Okay, and we see how it moves. Okay, so for example, we can put this thing is a cork, I think. Okay, as you say, it's a cork. Doesn't say it's a cork. Okay, but anyway, it's a very light object and it floats on the water and it tracks where a single piece of water moves in time, right? So in the next time, if we plot the water along the propagation direction, right? So if we go to the next time slot, basically the peak of the water propagates by a little bit towards right. Okay, and we see that this object also goes towards right and goes down a little bit. Okay, and if you give it a little bit more time, okay, the peak propagates even more towards here, and the object actually moves in a circular motion. Okay, it goes down and it goes back to the original position vertically. And then if we give it a little bit more time, then the peak of water will propagate more towards right, and then this small object goes up, okay, and it goes left, okay. And then if you look at the whole period, okay, look at the whole period. After a period of time, basically the another peak moves towards the original peak region. Okay, so this peak keeps moving towards right and moves to this original position. And then if we track the motion of this light particle, we can see that it is moving in a circle. Okay, so there is both a motion in the vertical direction, so it is a transverse wave, and there is a motion in the horizontal direction parallel to the propagation direction. So it is also a longitudinal wave. So water is both a transverse wave, and the water wave is both a transverse wave and longitudinal wave. Okay, this is a nice animation. You can see that the wave, if you track the peak position, the wave is moving towards right. This is a propagation direction. If you track a single particle inside this wave, is actually moving in a circular motion. So there's both transverse motion and the longitudinal motion. Okay. Okay. So we can call the front of the wave. Okay, the wave is propagating, and the first uh, we can look at the front of wave. We call it the wave front. Okay, the wave front of this water wave forms a circle. Okay, forms a circle, and the propagation direction is towards any direction in space. Right, it's radial, and the movement direction is basically a circle. Circle. Okay. Okay. So I think it'd be good to describe wave more quantitatively. Okay, so we talk about uh, period and wavelength. So what's the definition of wavelength? The wavelength is the distance over which a wave repeats. Okay, so if, for example, a wave like this in the space, okay, it repeats itself. If we look at the peaking here, there's another peaking here, so it repeats itself by this distance. Okay, so this is the distance between two peaks, and it's called a wavelength. Okay, you can also find other features. For example, the other obvious feature is this valley, okay, or trough. This valley is also displaced by a distance of lambda. Okay, so after a wavelength lambda, the wave can repeat itself. Okay, and if we track the wave, we define a time. Okay, how wave propagates in time. So we look at a single spot in the wave, and we track how it moves in time. We find out that after a certain period of time, which is this capital T, this spot actually moves to a equivalent position. Okay, so if we look at the wave at t equals t in here, and the wave at t equals 0, we see that we cannot distinguish the wave. Basically, the wave repeats itself also in time. Okay, and this period of time that the wave will repeat itself is called period. Okay, it's called t, capital T. Okay, and we can further define the speed of the wave, right? So if we look at, so basically the wave is a propagation basically of the peak, okay? And the peak is, there is a displacement in time. It keeps moving towards the right. And how much does it move? So if we give it a time of period t, it will move a distance of wavelength lambda. Okay, so if we divide lambda wavelength by period t, we will get the speed of the wave. Right? Okay, you can also look at this peak. Okay, this peak is also propagating towards right over time. And if you give it a time of period t, it will actually move a distance of lambda because the wave repeats itself after a period. Okay, so it travels the distance of wavelength. It takes a time of period. So wavelength divided by period is speed. And we can further define this quantity called f, which is frequency. Okay, so frequency is basically the inverse of period, right? So if we define the frequency as 1 over t, then lambda over t is basically lambda times f. Okay, so you can find out the speed of a wave by multiplying the wavelength and frequency. Okay, so this is a very important equation. Okay. Um, okay, so now we know the basic quantitative description of a wave. Okay, we know that there is a wavelength. Okay, the wavelength is the distance over which a wave repeats. There is a period. The period is time over which a wave repeats. There is a speed. The speed is basically wavelength divided by period. Okay, we can talk about different phenomena of wave. Okay, the first phenomena is the reflection. Okay, so if we generate a wave inside a string. Okay, we disturb one side of the string. We fix the string on the wall. Okay, we fix the string on the other side. We generate a wave. The wave will propagate towards right. But what happens when it hits the wall? It hits the wall. Actually, what happens is that when it reaches the wall, basically it will create some upward basically string will be something like that. Because it wants to move up, it will exert a force towards up, towards the wall, right? Because the wall feels this force, it will give a reaction force. Okay, and remember Newton's third law is that. Okay, I need a better drawing. Okay, so the wave reaches this fixed spot. It will give the wall a force towards up, and then the wall gives a reaction force which is pointing down. Okay, so action-reaction pair is equal in magnitude and opposite in direction. But we care about what the force that the wall gives to the string, right? So the force that the wall gives the string is pointing down. Okay, so with this force, actually, after the wave hits the wall, it will actually be inverted. Okay, so the wall will give a force and it will invert this wave, and then the wave will move towards the opposite direction, away from the wall. Okay, so this is how wave goes to the wall and then gets reflected. Okay, so if there is a fixed end, the wave will actually be inverted. Okay. And now there is a different case. Okay, so in this case, there is no fixed end. So we put the string on a ring, and then this ring can freely move up and down on this rod. Okay, so in this case, we have a free end. Okay. So now when the wave pulse reaches the end, it can actually still exert a force onto this ring, but then this ring can be freely moving. Okay, so this wave moves to here, and it gives a force to the ring, and then this ring can move up, right? This ring can move up, and then this ring can also fall down. Okay, this ring can also fall down. But the point is that in this whole process, this wave will not be inverted. Okay, so this wave is still pointing up, okay, and is propagating back. Okay, so if we have a wave and it reflects from a space, from a point, and this point is a free end, then the wave will not be inverted. Okay, but of course the propagation direction will be the opposite direction because it's reflected. Okay, so basically this is two types of reflection of a wave. Okay, if there's a fixed end, the reflection will be inverted. If the end is free, then the reflection is not inverted. If we can have a demo in here. Fixed end, then the wave is reflected and then inverted. Okay, we can have a slow motion. Wave propagates towards left. It exerts a upward force towards the fixed end. The fixed end will exert a downward force. Okay, it's action-reaction pair, and the downward force will make the wave inverted. Okay, and then it will be reflected back. Okay, now if we have a free end, then the wave will not be inverted, right? So wave moves towards left, it lifts up. Okay, this is very important. It has a free end, and it lifts up the free end. Okay, and then if we check it in time, the free end goes down, and the wave is reflected, but the wave is not inverted. Okay, the wave is still pointing up. Okay, so there's a distinction between the wave reflection at a free end. This is free end. It keeps positive, and then there is this thing, wave reflection at fixed end. Fixed end, it will be inverted because there is a force towards downward. Okay. And now we talk about the most important property and phenomena of a wave. Okay, and this property is called superposition. This phenomena is called interference. Okay, and this property is actually very straightforward. Okay, this property is saying that if we need to combine two waves, okay, we basically combine them algebraically. Okay, algebraically. Okay, so this means that we have a wave described by y1, which is this orange curve, and a wave described by y2, which is this green curve. And if we want to know the combination of these two waves, we basically add them together. Okay, and that's the resultant wave, which is y. Okay, and it's blue. And this property is called superposition. Okay, so we can have two waves at the same time, and what we actually see is a resultant wave. It's still a wave, but there is only one wave. Okay, it looks like there's one wave, but actually there are two waves in here, and they basically add up. Algebraically. Okay? And for example, we can consider those two waves, right? This one wave is described by y1. Y1 is basically a function of x. And this one wave is described by y2. Y2 is a function of x. And if we have two waves at the same time, we basically have a function of y as a function of x. We basically add those two things together. Okay, so we see that this wave goes to here, and then this wave goes to here. So the two waves can happen at the same time. Okay, this is called superposition. Okay, and I said this is probably the most important property of wave. But why is it the case? Why is it the case? It looks like too simple. The thing is more complicated when the waves are overlapped at the same spot in space, right? So now we consider two waves, okay, and they are propagating at opposite direction, okay? So again, if we want to have these two waves at the same time, we just add those two waves together. So we have this total wave, which is the sum of these two waves, right? But the thing gets non-trivial if these two waves are overlapped in space. So when they're separated in space, it's easy to understand. We just have one wave on the left, another wave on the right. But then if they meet at the middle, okay, we can see that the wave actually shows a larger amplitude. Okay, so the resultant wave is y1 plus y2, and because at this position, both y1 and y2 are positive. Okay, so y is larger than y1 and is also larger than y2. Okay, and after they meet in this spot, they can keep propagating. Okay, so because two waves can there can be a superposition of two waves, but we can also decompose them into two waves. Okay, so this wave is still in there. Okay, the wave propagating towards right is still in there. Wave is in here, part of this total wave, and then it keeps propagating towards right. Okay. On the other hand, the wave that's on the right propagating towards left is also in there. Okay. So after this time, when they interfere, it can keep moving towards left and then move towards left. Okay. So this is so-called superposition. Okay. So these two waves can happen at the same time. Okay. And they can happen at the same space. Okay. And probably something that's more striking is that if the waves is one of them is positive and one of them is negative, right? One of them is disturbance pointing up, one of them disturbance pointing down. And when they meet in space, we basically have, okay, I'm going to draw wave 1 in here, and then wave 2 in here, right? And when we add up something positive plus something negative, okay, we're going to see that uh, the resultant thing, if y1 is exactly equal to minus y2, is 0, okay, and it looks like there's no wave in here, okay, at this, but if you give it a little bit more time, okay, these two waves are still independent, okay, so the wave that's moving towards right are still moving towards right, okay, it exists at all times. Wave that's moving towards left, it's still moving towards left. Okay, it also exists at all times. Just at this specific time when the two waves overlap in the space, and they add up together to give you this interference. Okay, where the total wave goes to 0. Okay, at this specific time slice. Okay, so this phenomena is called interference. Okay, so wave pulses superpose as they pass through one another. Afterwards, the pulses continue on unchanged, right? So if the pulses combine to give a larger amplitude, this is called constructive interference. Okay, and on the right-hand side, there is a positive pulse and the negative pulse, and when they superpose, it gives rise to a destructive interference, where there is a moment where those two waves completely cancel each other. Okay, so y1 plus y2 equals 0 at this time, at this moment. Maybe this anime is more straightforward, so we can see that, okay, so although there are two waves and they can superpose, okay, they can superpose. Superposition is a property of wave, and it looks like at some moment that these two waves overlap in space and gives rise to a very large amplitude. This is called constructive interference. But after this moment, those two waves can still move independently. Right? Or throughout the whole time, you can say that those two waves are independent. They just move at their own speed. Right? But when they overlap in space, it looks like there is a large amplitude. And that is called constructive interference. I don't think we have a demo. Okay, so there is a checkpoint in here. Since waves add, does the resultant wave always have larger amplitude than the individual waves y1 and y2? Okay, so we have a wave y1, okay, and we usually describe this part as the amplitude. So this is y1, and we have another wave. And we usually describe this displacement as amplitude y2. Okay. So what is the resultant wave? So as we learned, the resultant wave is simple addition, right? So we have y1 plus y2. But does y1 plus y2 always have a greater amplitude? Okay, this is wrong, right? So if they are so both y1 and y2 can sometimes be positive and sometimes be negative. So if we add something together, okay, and if y1 is positive, y2 is negative, then the sum can be 0 or even negative, right? So if y1 is having a magnitude of a, which means y1 is between minus a and a, okay, and y2, wave 2 has a magnitude of a. Okay, now we add these two things together. So y1 plus y2 can basically range between 2a, positive 2a to negative 2a, right? And it can, there is a special value in between that's 0, right? So the amplitude, if you talk about the absolute value of this, it can actually range from 0 to 2a, right? So if we have two waves of the same amplitude a, then the resultant wave can take, the amplitude can take any value from 0 to 2a, right? So it doesn't have to be a greater amplitude than a, right? So if it's between a and 2a is greater than a, it's between 0 and a, and then it's smaller than a. Okay. We need to note that interference is a very specific phenomena that's specific to waves, and all kinds of waves will exhibit the interference effects. Okay, so it's not limited to waves on a string. And for example, we have this two circular waves, for example, water waves. Okay, and they're propagating towards different directions in space, so they form the wavefronts or the peaks of this wave form concentric circles, right? For example, if you throw something into the water, it will form this kind of water waves. Okay, if you throw two things into the water, you can generate two water waves, and each of them can be labeled by different color. One of the water waves is blue, the other water wave is red. Okay, and we can take a snapshot at a given time, and at this given time, we plot out all the peaks of the first wave, which is blue circles, and the peaks of the second wave, which are the red circles. Okay. If there are spaces in the spots in the space where the peak of the blue wave and the peak of the red wave overlap, then they will add up. Okay, so there are both a positive value. They add up to give you a larger value. Okay, so this gives you this constructive interference. Okay, we can determine that the constructive interference are basically along those positions. And we can look at all those positions, right? It's here, also here, also here. So basically, you can look at all the lighter regions. Okay, these regions are where the peak of one wave overlap. Sorry, the light radial rays. Okay, the lighter regions are regions where the peak of one wave meets the peak of the other wave. Okay, and in that case, we have a constructive interference. Right? We have constructive interference everywhere in here. Okay, here, 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 and here. Right? We have lots of regions with constructive interference. Okay, can we find the regions where there is destructive interference? The destructive interference means that the wave of one, the peak of one wave will meet the valley of other wave. Okay, or the crest of one wave will overlap with the trough of another wave. Okay, so if we look at it in space and label only the peak regions are actually different by by half of the wavelength, right? So basically, we see that there is a red wave peak, and then there is a blue wave peak, and then there is a red wave peak. There's a blue wave peak. There's a red wave peak. So this means in any space, in any spot along this line. Okay, in any spot. For example, this spot in the middle of two blue lines means that in here there is a peak, okay, of the peak. Sorry. Okay, we look at this spot, right? This spot in here. This spot in here. So this spot, there is, for the red wave, it is a peak. Okay, but for the blue wave, it is a valley. Okay, or the smallest value. Okay, a peak is also called a crest. Okay, they mean the same thing. And the valley can also be called as a trough. Right? TROUGH. Okay. So basically in here, the red wave is positive and the blue wave is negative. Okay, so if you add them together, it gives rise to a something like 0. Okay, so it's a destructive interference along those lines, And we can find other lines in here, right? So for example, if there are lines where they are different by half wavelengths, for example, this line, this is destructive interference. Okay, and for example, in here, we also have destructive interference. Right? And for example, in here, okay, we have destructive interference. Okay, so because if we look, we have red, blue, red, blue, red, blue, right? So the blue and red never overlap, but the peak of the red will overlap with the valley of the blue. Okay, so they destructively interfere. Okay, so in general, when waves combine, they can form interference patterns that includes regions of both constructive interference and destructive interference. So in this graph, we see that all the light regions or the light regions are constructive interference, right? And then all the dark regions between the light regions are destructive interference. Okay, so when waves interfere in space, they form interference patterns. This is a more straightforward explanation of constructive and destructive interference. Okay, so we have a wave y1, we fix it in space, and then we have a wave y2. Okay, we can put it everywhere different in space. Okay, so for example, at this point, okay, the peak of y2 will overlap with the valley of y1. The valley of y2 will overlap with peak of y1. Okay, so when the positive and the negative value add together, they basically give something 0. Okay, so we can see the resultant wave have a very small amplitude. So this is called destructive interference. You can also look at this bottom right part. Okay, so you have a wave in here, another wave in here. Okay, their valleys are aligned to peaks, peaks are aligned to valleys, and then they add up to give something 0. Right. Now, if we look at another time, okay, we look at another time. Okay, if we look at this time, basically all the peaks are aligned together, all the valleys are aligned together. Okay, so two negative values add up to give a large negative value. Two positive values add up to give you a large positive value. So you have a large amplitude of the wave. Okay, so this large amplitude is called constructive interference. Okay, so you can look at this graph, all the peaks are aligned to peaks, valleys aligned to valleys. Okay, we can also say that those two waves are in phase. Okay, in phase means that if we talk about the peaks are at the same position. Okay, so they're in phase. And in the destructive case, we can call it antiphase. Antiphase means that the peak and the peak are different by basically half a wavelength. Right? half a wavelength. In other words, the peak and valleys are aligned to each other. Okay, so they are antiphase. Okay, and we can, as I said, if you have two sources in the space, okay, they can each propagate along different directions, and each spot in the space will basically have different distance, okay, from those two sources, and basically there will be interference patterns in space. Okay, so suppose these two sources emit waves in phase. Okay, at point A, the distance to each source is the same. Okay, so source 1 will emit a wave and it travels to point A. Source 2 will emit a wave and it travels to point A. And originally they are in phase, so the peaks are aligned to peaks. And when they travel to A, they travel the same distance, so they are still aligned. Okay, so the peaks are still aligned with peaks, so there will be a constructive interference. Okay, and then there's spot B. Okay, the spot B, the distance from source A is greater than that from source 2 by half a wavelength. Okay, so when the wave travel from source 1 to B, it will travel half a wavelength more than the waves traveling from source 2. Okay, so if we label this wave 1 and label this wave 2, we'll see that they are displaced by half a wavelength. Okay, if we track the peak position, for example, this peak and this peak, okay, they are displaced by half a wavelength. So the distance, basically, if you call it P1, this is P2. We have P1B minus P2B equals half a wavelength. Right? So basically, the waves that travels from source 1 will go by half a period more. Okay, so that all the peaks in wave 1 will be aligned to the valleys of wave 2. So there will be a destructive interference at point B. Okay. At point C, there is also a distance difference. So P1C minus P2C is actually a full wavelength. Okay. So when the wave travels and the distance is differed by a full wavelength, okay, so the point in here is displaced by pointing here by a full wavelength, right? It's a full wavelength. But the peak will replace itself by a full wavelength. So it looks like these two peaks are just aligned to each other. Okay, those two waves are just aligned to each other so that the peaks are aligned to peaks, valleys are aligned to valleys. Okay, so those two waves will still constructively interfere. Okay. So at point A is a large value, at point B is 0, at point C is a large value. So there are interference patterns in space. Okay, something like that. So this actually has a special meaning in life, right? So if you have two sources of sound wave, okay, so for example, if you have a source of sound wave in source 1 and another source on the position 2, and you walk in space, you will actually find out that you will hear more sound at point A than point C, and you hear less sound at point B. Okay, why? Because at point B, there is a difference, okay, in the distance that the wave travels, and the difference is just half wavelength, so that there is a destructive interference and the amplitude of wave is small. So you hear less sound, although there are two sources playing music at the same time, right? Because they destructively interfere. Okay. Um, okay. As we derived, okay, if the path length from the two sources differ by integer times of wavelengths, then basically two waves are aligned to each other, and in this case, we will have a destructive interference. Okay, you can, for example, displace two waves by a single wavelength. Okay, you can also displace it by two wavelengths, right? And displace it by 2 lambda. And the wave basically will repeat itself, okay? So basically there will still be a constructive interference. And for destructive interference, you just need to displace these two waves by half a wavelength, okay? And after you displace it by half a wavelength, you can move the one of the wave by another wavelength, and the case is still the same, right? So you can have path length from the two sources differ by half lambda plus lambda, which is 3 half lambda, and half lambda plus 2 lambda. Okay, this is basically half lambda plus 2 lambda, and that gives you 5 half of lambda. So in these cases, the peaks are aligned to the valleys, and you will have a destructive interference. Okay. And the last thing we want to talk about in this lecture is standing waves. Okay, the standing wave is the wave that oscillate with time, but remain fixed in this location. Okay, so it looks like the standing wave doesn't propagate in space. Okay, for example, you have a string in here, it tied to the both ends, and you plug the string in the middle. Okay, and actually you will see a standing wave. Standing wave means that if you track the peak of the wave, okay, this is the peak of the wave, it doesn't propagate towards right or towards left. Okay, so in the next time slice, you will not see a peak like that. You will not see a peak like that. Okay, what you will see is that everything is basically moving up and down. Okay, but there's no propagation of wave. Okay, so the peak of the wave will stay at the same position over time. And this kind of wave is called standing wave, the standing wave. And we can see that basically we're tying the two ends of this wave onto these two walls, right? So this is a left wall, and this is a right wall. And if we consider the full wavelength, okay, if we consider the full wavelength, this wave between the two walls, basically half of the wavelength, okay? And there is another half basically somewhere here, right? So this is a full wavelength of wave. So the wavelength of the wave basically 2 times the distance between the wall. Okay. And how does a standing wave form? Okay, so actually, although the standing wave looks like it's not propagating in space, it's actually consisting of 2 waves, and each wave is traveling. Okay, and they are there is a superposition of these 2 waves. So in this right graph, basically we have a standing wave that is brown. Okay, and we have different moments in time. Okay, and we can see that this brown wave is not propagating in space. So we look at these dashed lines. Those labels the peak position of this brown wave, and we can see that the peak position doesn't move in space. Okay, the valley position also doesn't move in space. Okay, at different times they always at the same position. Okay? But if we look at this red wave and blue wave, okay, if we add them up, it gives rise to this brown wave, but each of them is propagating. Okay, so the blue wave is propagating towards right. Okay, if we track the peak of the blue wave, it's in here, and after some time it's in here, so it moves towards right. Okay, so after some time even here. Okay, keep tracking. Blue wave moves towards here. Okay, it keeps moving towards right. Okay, and if we track the peak of the red wave, for example, the red wave was in here, and it goes to here, peak goes to here, here, dash line, and left to the left of the dash line. Okay, so you see that the red wave is actually moving towards left. Blue wave is moving towards right. Okay, but if we add them up, we actually form a standing wave where if we track the peak position, it doesn't move in time. Okay, it's always staying at the same position. So it's called a standing wave. Let's look at this demo. It will be more straightforward. So you can see that there is a so this looks complicated, but you can look at it separately, right? So you can first look at this purple wave. Purple wave, the peak position is not moving in time, right? The peak is always at the same position. And looks like this wave just goes up and down, goes up and down, if you look at the purple wave. And now you look at the two waves that add up to this purple wave, which is the red wave and the blue wave. Okay, so red wave plus blue wave equals the purple wave. But if you look at the red wave, you can obviously see that the peak is moving towards left. Okay, sorry, the red wave, the peak is moving towards right. And if you look at the blue wave, you can obviously see that, okay, let's start from the beginning. Okay, start from the beginning, we see that the red wave is moving towards left, the blue wave is moving towards right, and they add up to give you this purple wave. Okay, and in here, okay, I think they secretly changed the direction. The red wave is now moving towards right, the blue wave is moving towards left, but they still give rise, add up to this purple wave. Right? So we have two waves propagating at opposite directions, and they add up to give you this standing wave. Standing wave, the peak doesn't move in space. And we can study the standing wave more quantitatively. Okay, so there are 2 points that we know for the standing wave because there is one end on the wall, the other end on the wall, they are fixed in position. Okay, so those 2 points, we know they will stay at these points. But if we look at the standing wave, there could be other points which are always staying at this in the middle position. Okay, for example, for the second harmonic standing wave, there is a point, okay, that stay fixed. This is called the nodes. This is called the nodes. And for the third harmonic, there is this point is a node, and this point is a node. So when the wave is oscillating in time, it they are oscillating like this, but then all those points, all those nodes will stay fixed, and then halfway between any two nodes is a point that has maximum displacement. Okay, for example, this point can have a maximum displacement. If this is a maximum displacement, and this point is called an antinode. Okay, so we can see that in second harmonic, that's this point and this point, right? In third harmonic, that's this point, and this point. And we see that in any harmonic, it's always like node, antinode, node, right? So they are coming in the alternating ways, node, antinode, node, antinode, node. And there are infinite numbers of standing waves, and each mode is called a harmonic. Okay? And the frequencies are integer multiples of the first harmonic. Okay? We will derive this soon. Okay? So if the first harmonic has a frequency f1, then the second harmonic has a frequency of 2f1, and third harmonic has a frequency of 3f1. Okay? How do we derive this? How do we derive this? So we can start from the first harmonic, or we call it a fundamental mode. Okay, fundamental mode. The fundamental mode has the lowest frequency, right? So we derive that this full wave is basically of a wavelength of 2L, right? This is the wavelength of this wave, and the wavelength is basically L plus L is 2L. And then if we talk about the frequency, okay, we said that the frequency times wavelength is speed, right? Because speed is wavelength divided by period. Okay, after a time period t, the wave repeats itself in space at a distance of lambda. Okay, and 1/t is frequency. Right, so speed is frequency times wavelength. So if you want to know the frequency of fundamental mode, you divide the velocity by its wavelength, and wavelength is just 2L. So v divided by 2L is the frequency. Now let's move to the second harmonic, right? The second harmonic, it basically has a full wave, right? So there is this, and it goes here, and if you keep drawing, it will repeat itself, right? So from the left wall to the right wall is basically one period or one wavelength of this wave. Okay, so the wavelength equals the distance between walls, and the frequency is just v divided by L, and we can see that it is 2 times the fundamental frequency, because fundamental frequency is just v divided by 2L. Okay, so second harmonic is 2 times the fundamental frequency. Now look at the third harmonic. We see that there is one wavelength. There's one wavelength from here to here, and then there is half wavelength. Okay, so basically between those two nodes, we always have a half wavelength, right? Between two nodes, we also always have half wavelength. And third harmonic basically have 3 times half wavelength. Right? So 3 times half wavelength equals the distance between walls. So the wavelength is just 2/3 of L. Okay. Now if we derive the frequency we divide the velocity, the speed by the wavelength, we get that it is 3 times v divided by 2L, and is 3 times the fundamental frequency. Right. So, okay. So if we are talking about first harmonic again, first harmonic, there is only one half wavelength between these two walls, right? So the wavelength is 2 times the distance L, and the frequency is v divided by 2L. Okay, now if we look at the nth harmonic, we basically have n times half wavelengths between these two walls, right? N times this half wavelength. For example, fourth harmonic will have 4 half wavelengths. Okay, so n times half wavelengths equals the distance between the two walls, right? Distance between the two walls is L. And from there, we derive that the wavelength is basically 2L divided by n, right? Wavelength is 2L divided by n. And the wavelength is basically the fundamental wavelength lambda 1 divided by n. And if we look at the frequency, frequency is v divided by wavelength, right? So we find out that it is n times n v divided by 2L, and it's n times the fundamental frequency. Okay, so the first harmonic frequency and the wavelength we know, and then the nth harmonic, the frequency is n times, the wavelength is 1/n. Okay. And at the end, we have a demo. Okay, so we have a string, and we're actually showing you the standing waves. So this is a long string, and 2 ends are fixed. Okay. And now we try to generate a standing wave inside. So we tune to the first harmonic, or the fundamental. We see that there is basically half wavelengths between those two fixed points. Okay, half wavelengths. There are two nodes at the two sides, and then there is a antinode in the middle, right? So now we tune to the second harmonic. The second harmonic, we will have two half wavelengths, right? So at two ends, we still have two nodes. At two ends, we have two nodes, and in the middle, there is a node. There's also a node, right? So pay attention to this point, right? This point doesn't move in space. Right? It's a fixed point. And then we have two antinodes in here. These two positions, there is a maximum displacement. So node, antinode, node, antinode, node, right? And in here we have half wavelengths, and in here we have half wavelengths. Okay, something like that. Okay, now we tune to the third harmonic. Okay. Third harmonic, what is the third harmonic? That is third harmonic, right? So in the third harmonic, again, there is a node, there is a node, okay, and between those there are antinodes, antinode, antinode, and of course at two ends there are also two nodes, okay, and here is a half lambda, here is another half lambda, and there is another half lambda, okay, they're all half lambda. Let's look at it. This is third. This is third harmonic. Fourth harmonic. What is fourth harmonic? If this is a fourth harmonic, same thing, okay, right? Here's a node, here's a node, here's a node, and here is half lambda, here is half lambda, here is half lambda, and then here's half lambda, right? Here's also two fixed points or two nodes. Okay, something like that. Okay. And the last thing we want to mention is that this is one-dimensional standing wave. Okay, if we have a two-dimensional space, we can also have a standing wave. And the way we show it is that we can have those metal plates is vibrating, and it's vibrating and generating a standing wave. And then we can put salt crystals in there. Okay, and when the plate is vibrating, then the standing wave develops, and the salt will be collected at the nodes. Okay, so when the plate is not moving, the salt will be staying in the position. When the plate is moving, the salt will be kicking towards the positions where the positions of the nodes. Okay, so the wave pattern is shown by the salt being at the nodes. Okay, and standing waves on two-dimensional plate is pretty complex, but we can appreciate its beauty. Okay? So we can probably find a video in the YouTube, okay, standing wave two-dimensional. And we can look at those salts, right? So when it starts to vibrate, okay, there are antinodes where the salt vibrates a lot, and there are nodes where the salt doesn't move. Okay, and the nodes will collect all the salts, and the salt will show you where the nodes are in the two-dimensional plane. And the different modes, again, have different frequency. You can look at it on the bottom right side. Okay, we have different two-dimensional standing waves, and they have different frequency and different pattern in the space.